We let AI run so much of our lives, our music, our driving directions, even medical stuff. But have you ever stopped to wonder, how do we actually know we can trust it? How can we be mathematically sure an AI is going to get it right? Well, today, we're going to crack that code.
Right. This is the big one. This is the whole ball game in machine learning. You give your model 1,000, maybe 1,000,000 pictures to learn from, a tiny little snapshot of the real world, but then you expect it to work flawlessly out in the wild on billions of new things. It feels like a total leap of faith, right? But what if it wasn't? What if there was a way to turn that leap into a step you can measure?
There is, and it's got this wild name. Probably approximately correct learning. Yeah, I know, it sounds like a mouthful, maybe a little intimidating, but trust me, we're going to break it down and you'll see it's actually one of the most elegant and powerful ideas in all of computer science. We just call it PAC Learning, for short.
So let's just tackle the first part of that name, approximately correct. Here's the thing about machine learning. It's not about being perfect. In the real world, perfection is basically impossible. The goal isn't to be flawless. The goal is to be really, really close to the best possible answer you could ever hope to find. And to measure how close we are, we use this idea called estimation error. It's actually pretty simple. It's just the gap between how well our model did and how well the absolute best God-tier model could have possibly done. Our job is to shrink that gap until it's tiny. This visual just nails it, right? That red dot at the bottom, that's the theoretical best, the lowest error anyone could ever achieve. Think of it as the gold medal. Now, the blue dot, that's our model. That's the one we actually built from our limited data. The distance between them, that's our estimation error. And in the world of PAC learning, we give that little gap a name epsilon.
So our first mission is to put a leash on that epsilon. We want to be able to state with mathematical proof that our error is guaranteed to be less than some small number that we get to pick beforehand. Maybe we say, I want my model's error to be within, say, 1% of the best possible. We're aiming to be approximately correct.
Okay, so we want a small error. That makes sense, but there's a catch. We're training on a random set of data. What if we just got super lucky? Or even worse, what if we got a really weird, unrepresentative sample? That brings us to the second part of the puzzle. This is where the probably comes in. Think about it. The data we feed our model is just one random scoop out of an ocean of possibilities. We could have easily scooped up a sample that makes our model look like a genius in training, but then it totally faceplants when it sees the real world. How do we guard against that?
Well, PAC Learning is brutally honest about this. It says, look, you can never be 100% certain. Just forget about it. But, and this is a huge but, we can get a guarantee that is highly, highly probable. We can get to a point where we are, say, 99% sure that our model is as good as we think it is.
This graph shows you exactly what that means. It shows all the possible error values we could get, depending on the data we happen to sample. You see that long tail on the right? Yeah, it's possible to get a really bad error if we get a disastrously unlucky set of training data. But the vast majority of the time, our result is going to land in that big, safe, red shaded area, the good zone. And that tiny chance of being unlucky? We give that a name too, delta. It's our probability of failure, the risk we're willing to accept. We might say, okay, I'm comfortable with a 1% chance, a delta of 0.01, that I got a bad sample and my error is actually bigger than I'd like. We get to choose our own confidence level. So we've got our goals all set up. We want an error smaller than epsilon, and we want a probability of failure smaller than delta. So how does the computer actually pull this off? What's going on under the hood? Well, the main engine for this is a fancy-sounding thing called empirical risk minimization, or ERM. But honestly, the idea is super simple. The algorithm just looks at all the possible models it's allowed to choose from, and it picks the one that makes the fewest mistakes on the training data you gave it. That's it. It just minimizes the errors it can see. And the reason that works is because of this one beautiful core belief. The whole theory rests on this. If you gather enough data, the error you see in your little sample starts to become an incredibly good reflection of the error you'll see out in the real world. Your small world starts to look just like the big world. And this isn't just a hunch. It's backed by some heavy-duty math called the uniform law of large numbers. Just look at this graph. When we have very few samples, our confidence is all over the place. But as we keep adding more and more training data, our confidence that the error is low just skyrockets towards 100%. More data literally buys us more confidence. Okay, so this is where it all clicks into place. We know what we want, a small error, epsilon, and a small risk, delta. And we know that the more data we have, the more likely we are to get it. So the obvious next question is, how much data is enough?
And this is the real magic trick of PAC Learning. It's not just a bunch of nice ideas. It gives us a cold, hard formula. It's a formula for something called sample complexity, and it tells you the exact number of training examples you need to collect to get the guarantees you want. So let's just quickly break down the recipe. You tell it your epsilon, how accurate you need to be. You tell it your delta, how confident you need to be. And you tell it this thing H, which is basically how complex your model is. Is it only learning simple straight lines, or is it learning really complicated squiggly shapes? You plug those three things in, and the formula spits out M, the number of samples you need. It literally tells you the price of confidence measured in data.
And to show you this isn't just theory, let's run the numbers from the source material. Let's say we want our error to be less than 5%, and we're okay with a 10% chance of failure. For a model with a certain complexity, the formula tells us we need about 5,673 training examples. Not around 5,000, not a few thousand, a specific, actionable number. Okay, prepare to have your mind blown a little bit, because the most incredible, most powerful part of this whole thing is that this guarantee, it works no matter what your data actually looks like. It is completely distribution-free. Seriously, think about what that means. It means if we're trying to learn from data about people's heights in Prague, which has one particular shape, or data from Delft, which has a totally different shape, the formula gives us the exact same guarantee. We could even use data from Timor-Leste, where the data looks completely different again. The math doesn't care. The PAC guarantee holds true without needing to know a single thing about the underlying data. That is an absolutely insane level of confidence. So let's put it all together one last time. PAC Learning. It means our model is probably correct because we're highly confident, like 99% sure. It's approximately correct because its error is guaranteed to be super close to the best possible. And it's correct because this isn't just a guess. It's a real mathematical guarantee for machine learning. What this framework does is it turns building AI from a kind of dark art into a repeatable science. It lets us calculate the exact price of confidence. And that leaves us with a really deep question. For a self-driving car, for an algorithm that detects cancer, for an AI that trades billions of dollars, what's the right price to pay? How much certainty is ever really enough?